So we're now going to take a look at another example, and this one's going to show the limitations of using inherently sequential Java streams operations, such as iterate and limit, in the context of parallel streams. So this kind of covers the topic of, just because you can doesn't mean you should. And so, as is often the case, just because it's possible to do something doesn't mean it's the right thing to do. And we'll kind of talk about that, and you'll see how it works. So in this particular case, we're going to be computing some interesting values. We'll talk about what they are in a second. And we have a field here called S number, which is set to 1,000,000. So we've got 1,000,000 iterations for this particular test. And then down here, we're going to make it possible to override the number of iterations if we so choose by the command line argument. We then go ahead and make ourselves a new object of type ex15, which is the test number. We warm up the thread pool, and then we're going to run a couple of different variants of tests. So we're going to run a parallel version of test stream iterate, which we'll look at, and we'll see how it performs. And not to spoil the surprise, it's going to perform very poorly because the methods we're going to look at, iterate and limit, are really inherently sequential and don't split efficiently and evenly and have other problems because under the hood, they have to manage mutable shared state, which has to be synchronized, et cetera, et cetera, et cetera. So we'll take a look at the parallel version and the sequential version of those stream iterate mechanisms. And then we're going to look at a different set of mechanisms that use the sequential and parallel variants using a range instead of an iterate operation on a stream. And we'll see that that performs way better than the iterate because range splits efficiently and evenly, quite nicely. So as before, we're going to go ahead and start running the tests. They don't take very long to run, and we'll come back here in a second and take a look at what they mean. So let's take a look at test stream iterate. As you can see, it takes a Boolean parameter to indicate whether we run it in parallel or not, and the number, which is the number of even numbers we want to find. And here's what we're going to do. We're going to generate a stream of numbers starting at 2. So we're going to use the iterate factory method, which generates an indefinite sized stream. It will go on forever if we let it. Start with the initial value of 2, and every time we're going to add 1 to the initial value. And then we come down here and we say, if we're running a parallel stream, then go ahead and make the sequential stream parallel, because of course, it's going to start out by being sequential. Stream.iterate gets us a sequential stream by default, which is a good thing, as you'll see. And then what we do here is, once we've either enabled parallelism or not, we're then going to remove all the odd numbers from the stream, but we're going to limit the number of elements in the stream to whatever we passed in as the parameter. So if we pass in whatever we pass in up here, S number, you can see that this is the number that we're going to limit it on. So it's a large number. It's 1,000,000. And we're going to limit it by 1,000,000. And then after we've got the first 1,000,000 elements, we're going to go, or as we get the first 1,000,000 elements, we're going to compute the square root of each even number in the first n elements. And we collect that into a list. And then we stop the timer, and then we print out how much time it took to do this, either in parallel or sequentially. Down here, we do the same logical thing. We compute the same number of values, but this time we're going to end up doing it with a range operation. So the range operation is another stream operation, which is, in this case, we're going to take the value 2, and we're going to take the number, multiply it by 2, and add 1. So we know we're only going to go for the first n even numbers. And so we pre-compute how many we'll have to look at to get even numbers out of this thing. And then we conditionally either run it in parallel or not. We come down here and we remove all the odd numbers. And by the way, I should have explained this earlier. This is a little helper method that takes a number and uses a bitwise operator to determine if the number is even or odd. So we're checking to see if it's even. So we're modding it by 1, and if it returns 0, then we know it's even. So we only allow even numbers through, and we find the square root of them, and we collect the results into a list. So were we to run this thing, or we did run this thing, you can see some interesting results. You can see that the sequential stream took 89 milliseconds to find the square root of the first 1,000,000 even numbers, whereas the parallel stream took 336 milliseconds to find the square root of the first million even numbers. So this is, sort of wildly non-intuitive at first glance, because you're like, well, wait a second, you've got this, you just told us you got this honking 8-core hyper-threaded, Mac with ridiculous amounts of memory, and you turned on parallelism and it slowed down by like this enormous amount, right? It slowed down by like a large factor, like a factor of 4, basically. What the heck is going on? Well, what the heck is going on is that iterate and limit don't work well with parallel streams because of their semantics. And so as a consequence, you should not use iterate and limit with parallel streams unless you absolutely have to. And the main reason there is that the shared mutable state issue has to be synchronized to figure out when you've reached the limit in a parallel stream. Conversely, you can see when we use the sequential stream on int range, it took 37 milliseconds to find the square root of the first million even numbers, and it took 85 milliseconds to find the square root of the first million even numbers with a parallel version. And that's kind of an interesting result. So just for kicks, let's go up here and let's see if we can get a different result if we change it to 2 million. So now we're going to generate 2 million of these things, and we'll see if we see better results. And well, sort of. So you can see that now the parallel stream version is better than the sequential stream version by quite a bit, but it's still slower than the sequential stream version for the range operation. And so, just for kicks, let's keep making n larger and larger. And of course, poor iterate is really going to suffer now. But at some point we might expect to get a break even. Yeah, look at this. This is interesting. So you can see that parallel streams are just getting slower and slower as we increase the number of elements we're looking for. And now sequential stream and parallel stream are running roughly the same amount of time. And that's because n is finally getting big enough that we're getting a benefit by parallelizing things relative to just doing the computation sequentially. So this, again, is just a great example of the n times q stuff. So as n gets bigger, right now we cranked up n to 5 million. Now you can see we're finally starting to get benefits of doing this. And I think one of the things going on here is that the q, finding the square root, is a pretty fast operation. So we're not really getting that big of a bang of our buck from using parallelism. So n has to get really big before we're actually going to get a benefit of using parallel processing. So anyway, that's just a fun example to kind of, once again, demonstrate a few important facts about streams and parallel streams. Make sure you know the operations that you're using and know whether or not they parallelize effectively. And then also be sensitive to the fact that the n times q model can have an impact on deciding when it's worthwhile to do parallel processing. And of course, the great thing about this example, just to make that point even more clear, is that we wrote the code to make it trivial to parameterize whether we're running in parallel or not. And so by writing code with this little pattern I'm showing you here, we're basically able to make our mind up based on experimentation. The code stays the same, and then we can decide how we want to run this, whether we want to do it parallel or sequentially, based on empirical knowledge that, of course, is often very dependent on characteristics of your hardware and your processor caches and the number of cores you have and how much memory you've got, and what version of the JVM you're using, blah, 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 all that kind of stuff.